basically, if we do a higher level, any loop in the lower level will be collapsed into one instruction when we handle the analyze the higher level. Then we go down. So the first step in Tupni is we identify constraints. The basic idea is we leverage symbolic predicates. Here's a simple example. As we see this instruction, move the first 2 bytes into AX, add the next 2 bytes onto AX, then compare it with 5. With the dynamic data flow analysis, we can derive a symbolic predicate saying, oh, the first 2 bytes plus the second 2 bytes must equals to 5. And so this gives us a symbolic predicate. And with the symbolic predicates and other techniques, we can infer 4 kinds of constraints, such as length fields that specify the size of a record sequence or the size of a buffer, or a value constraint on single field. For example, saying the type must be 1 or this ID must be 5. Functional constraints on multiple fields, for example, like checksum. The checksum specifies saying the XOR of all the fields in the header must equals to the checksum field. And also intermessage constraints is we track the dependencies between the input message and the output messages. At the end, after we analyze each single input, we will output the format as a BNF rules in a top-down manner. For example, we first start with the root rule at the top level, tells us what the input consists of. Here, in the running example, we see that the first field specifies the number of records, then it followed by a record sequence. Here is sequence, and the F1 says the size of a sequence is decided by F1. Then, for each record sequence, we'll have an alternation rule that enumerates all the record types we identify in Tupni. Then for each record type, we will enumerate the fields in each record type. And actually, this process will recursively being done because each record type may have a sub-record sequence. We just continue doing it recursively. An important step at the end of Tupni is to generalize the formats over multiple inputs. Here I will show you a simple example. Based on the running example, we may derive 2 formats. They are different. And to merge them together, get a generalized format, we first align all the rules. That means all the top level rule, all the record sequences, and all the record types. For the top rule, we just compare them and put them together. And for record sequences, actually, it's 2 things I want to say is we have a very easy way to align record sequences because we can use where's the loop, the instruction pointer of where the loop starts. We use that instruction pointer to find to specify the record sequences. Once we find align the 2 record sequences, we just simply merge them as alternation rule. For example, in the first running example, we see 2 types, and in the second one, we see the third record type, and we just merge them together. Then we continue this process to merge all the record types. So we implement a Tupni system, a prototype based on Vigilante and IDNA. IDNA is a tool inside Microsoft that allows people to record this execution sequence. And excluding Vigilante IDNA, we have 14,000 lines of C++ code and 4,000 lines per. We test on Tupni on 10 formats, and some of the files, some of the network messages. At the end, we generate a high-quality format for all of them. So I just want to give details on one metric. Here we show that on the 10 formats, we identified all the record sequences based on the second row. Let's say Mr. sequence is 0. And the third row showing here is wrong sequences. We identify some wrong sequences. The reason is sometimes applications use a loop to process input. However, those input fields are not a record sequence. For instance, there like a JPEG parser use a loop to compare the first some 4 bytes in the input to see if they equal to some specific value. for this kind of case, we may have wrong sequences. I'll skip this slide. This slide basically tells other experimental results. For example, we have no misclassification error of record types because the condition we use is sufficient. But some records of the same kind may be classified into different types because it's not necessary. So same record type may be treated processed by different execution sequence, but the inflation is very small. Here's an example to show on the left hand side as a format we can derive from Tupni. On the right hand side as the documented format we put manually. We can see that we identify all the fields and the constraints with a high accuracy. So I just talked about Tupni. I ignore some experimental results details. Next, I will tell you about how in ShieldGen, how do we generate probes and analyze them. Just go back a little bit. The goal of the ShieldGen is to automatically generate a data patch for unknown vulnerabilities given the attack instance and the format. The key idea, if you recall, I said 20 minutes ago, is we want to construct a new attack instance based on the initial attack and the format. And we feed the attack instance to an oracle and decide if that new attack instance will trigger the attack. We'll continue that process until we find the vulnerability signature. So for zero-day attack detector, in ShieldGen we use a vigilante, and for data analyzer, if the format spec is available, we'll just use GAPA. If the format spec is unavailable, we can use Tupni to reverse engineer the format of the attack instance. And next, I will focus on this probe generator and analyzer. The basic ideas for probe generator and analyzer is to construct, first we construct this so-called attack-specific initial vulnerabilities predicate. Put another way is we just use the original attack instance as a signature. The problem with that is too specific. Any small changes on that won't be detected by that signature. And then the next step is we generate probes to the zero-day attack detector and to make the predicate vulnerability specific. In other words, is we try to relax the conditions we have in the initial vulnerability predicate. We face two challenges here when we construct the probes. First is how to generate legitimate probes. The second is how to reduce the number of probes. First, I want to ask questions why we only care about legitimate probes. The reason is illegitimate probes should be dropped either by the application or by the input filter. So we don't want to generate invalid probes that will lead us to wrong result. And the key idea about generating legitimate probes is to enforce constraints on various fields based on particle semantics. For example, if you recall, in Tupni, we want to enforce the constraints on the input, saying, oh, this is a checksum field. Every time when I change the certain fields depending on this checksum, we need to fix the checksum too. And also the length field, like specify the size of the record sequence. So we enforce this constraint so that we'll get a legitimate probes. And the second challenge is to reduce the number of probes. Our key ideas in ShieldGen is to first we want to remove all the irrelevant iterative records. Second is we want to eliminate illegitimate probes. And the third one is we focus on the last network message. The reason is given a message sequence that will trigger the attack, basically most oftentimes the vulnerability sits in the code for handling the last message. And the data analyzer can track the protocol context so that we only care about saying the protocol state is this and the message look like that. So that will trigger the vulnerability. And so we're only checking the fields in the last message.